All right, welcome everyone to Wednesday Night at the Lab. My name is Dylan Brewer, and I'm a student worker here at the Biotech Center. On behalf of the Biotechnology Center, UW-Madison Division of Extension, Wisconsin Public Television, Wisconsin Alumni Association, and UW-Madison Science Alliance, welcome to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it is my pleasure of welcoming Justin Vanderburg with us tonight. He's going to be sharing about IceCube detection of neutrinos from a galaxy nearby. Before we get started, we're going to ask him the infamous 5 questions.
Before we get started.
Before we get started. Justin, where were you born?
I was born not just in LA, but in Hollywood on Sunset Boulevard.
Wow, okay. And where did you attend high school?
I went to Evanston Township High School in Evanston, Illinois.
Awesome. And where did you go for your undergrad degree?
Stanford.
Stanford. And what did you study at Stanford?
I studied physics with a math minor.
All right. And where did you go for any advanced degrees?
I went to UC Berkeley for my PhD.
Awesome. All right, everyone, please join me in welcoming Justin.
Good evening, everyone. Can you still hear okay in back? Yep. Great. It's a pleasure to be here tonight to tell you about an experiment I work on along with some of my colleagues, some of whom are here in the audience, called IceCube, which is headquartered here in UW-Madison. And the neutrinos that we've detected, specifically neutrinos from a galaxy nearby. And I'm not a big sci-fi fan, but I know some basics of sci-fi, so that might ring a bell from familiar stories. So the players in our story tonight are 3 main ones. One is the IceCube detector that I'll tell you all about. This building here is where all the signals from IceCube, which is buried deep in the ice at the South Pole, come together into basically a giant computing building, which is this building here. Another player is this swatch of sky above, the swatch of light and dust and gas above the sky, above the ground in the sky. Anyone know what that is? The Milky Way, yeah. A friend in grad school was a moderator for Wikipedia, and one of the most contentious arguments he had to moderate was whether the Milky Way is a swath of stars in the night sky or the galaxy that we live in. And that was really contentious for some reason, but it's both, of course. Yeah.
Do you have your mic on?
I think I do. Should we turn it up?
It's hard to hear you at this point.
Okay. Is the mic all the way up? Could you maybe turn it up for people in back? Can you still hear okay? All the way in back sounds okay. Okay.
Very low volume.
Maybe if you could turn up the volume if that's possible. Okay, and the third player in our story, which is a little bit involved, is this green glow, which is produced by energetic particles hitting our atmosphere, the aurora. Okay, so neutrinos from a galaxy nearby, but we're going to start with an even more familiar sounding story, which happened a long time ago in a galaxy far, far away, and that's because it's chapter 1. So we're going to have, this is a short one, this is kind of a prelude, but we're going to have 3 chapters tonight, so this is chapter 1 of our story. So what happened a long time ago in a galaxy far, far away? Here's the galaxy far, far away, and it emitted starlight. So you can see this beautiful galaxy, it's like this spiral shape, it's got lots of stars, it's got dust, you can see these black dusty parts. It's got these bright glowing parts. That's probably where young stars are being formed rapidly. Some of them are living fast and dying young and burning out in supernovae. Really a really beautiful, energetic place. And that's just looking at the main parts of the galaxy. If you look at the inner part, there's also a giant black hole at the center of that galaxy. And it emitted also a giant amount of light, comparable to the amount from the entire galaxy from all the stars. Not only that, the light from the stars and from the black hole at the center, that also emitted neutrinos. We'll get into what neutrinos are, but that's one of the exciting discoveries that I'll show you today. Okay, so the basic question. So we've said what happened, basic storytelling. We also need to talk about when and where. That is, how long ago? The answer to that is 50 million years ago, this light was being emitted, and these neutrinos. And that leads to the first audience participation of the night. How far away do you think this is? Yeah. 50 million light years. It almost feels like cheating, doesn't it? Should we pass that answer, or should we call that cheating? Accurate? Okay. Yeah, so here's a hint if you didn't know that. You guys are advanced. Hubble captured this image. So that means that it was taken within the last 30 years or so, 30 years. And so that means that the light traveled 50 million minus 30 years to get to us. That means that the distance away is 300, 300, 000, 000, 000, 000, 000, 000, 000 miles. So for full credit, that's the full answer in English US units. To put it a little bit more compactly, that's 300 million trillion miles. That's still a mouthful. And so that's why we use, in astronomy, we use these more convenient units, 50 million light years. So the light, how long ago was it emitted? 50 million years. From how far away? 50 million light years. So a light year is a unit of distance. It's really convenient because you can give the answer to that kind of question immediately without needing to do these calculations or count the number of zeros. So some of you know that concept between years and light years right away, but let's review that for people who are not familiar with it. Oh yeah, the name of this galaxy, by the way, is Messier 77, also known as MGC 1068. This is going to come back into our story in a bit. It's part of the Messier catalog, that's why it's named Messier 77. Messier was a French astronomer who cataloged about 110 of the brightest objects in the sky that he could see in the 1700s, pretty long time ago. So that means that it's a really important galaxy. It's one of the 110 basically best known objects as of the 1700s. Okay, so let's go over this concept about this relationship between distance and time. So light travels really fast, much faster than sound, but it does not travel instantaneously. Did any of you experience this last night? Something similar? Light travels really fast. What else travels really fast but not instantaneously? Lightning, yeah. Neutrinos? Sound. Yeah. You might have you might have experienced an analogous situation. Last night I was watching fireworks in Monona. Here's a picture I took of them. And to experience the full fireworks show, it's nice to be able to both hear the explosions and see them. Both light and sound, that's the full experience. And so sometimes you notice, if you're paying close attention, that the flash happens and then you hear the bang a little bit later, kind of like lightning that someone mentioned. So let's do a little bit of math with this. So the sound speed, sound travels through the atmosphere at about, in round numbers, 800 miles per hour. If you prefer metric, that's 0.3 kilometers per second. Light speed, on the other hand, is much faster, about 1 million times faster. So 700 million miles per hour the light travels, or 300,000 kilometers per second. So if, for example, a firework explodes, if you're pretty close to under it and it's going pretty high up in the sky, a typical distance is about 1,000 feet, or a third of a kilometer. That means that the explosion happens, the light arrives, you just combine the distance, 0.3 kilometers, with the speed of light, 300,000 kilometers per second, to get the fact that the light arrives almost instantaneously, just a millionth of a second after the explosion. And then you have to start waiting for the sound to arrive. So the sound arrives now 1 second after the explosion. So that's traveling at 0.3 kilometers per second, and it's 0.3 kilometers away, so I chose simple numbers. It takes a second to travel to you. So you can often see and experience this delay. The light feels instantaneous, but the sound is delayed. And you can even use this to measure the distance to the explosion. So in this case, because of that second delay between the light and the sound, you can calculate that it's about 1,000 feet away. And that's the rule of thumb that people use also for lightning. It's the same idea. The light travels to you very quickly, and the sound is delayed by that same delay time, the speed of sound. You can use that to calculate how many feet away the lightning happened. Okay, so we can also use this to define a useful unit of distance. So if sound travels at 0.3 kilometers per second, then 0.3 kilometers or 1,000 feet is equal to 1 sound second. So that might be a useful rule of thumb for measuring the distance to fireworks or to lightning. 1,000 feet or 1 sound second. Another useful thing I want you to take away from this example is to imagine experiencing fireworks if you could not see them or could not hear them. It might still be a really interesting show. You'd be able to hear all these booms, or you'd be able to see these beautiful flashes, but it wouldn't be the full experience. You wouldn't get to know everything about how big the explosions are from the sound. Sometimes there's one that's not that bright but has a really big boom. Vice versa, sometimes there's one that doesn't make a very big boom but makes a dazzling light display. Maybe lots of different colors, and the colors might tell you things about the chemicals that were in the explosion. So you really need all the different pieces of information to fully understand the situation. So that means that light and sound are different messengers. They carry different pieces of information. So that's going to be a theme tonight. So building on that example, the idea of a sound second is light traveling. So now light travels much, much faster than sound. In the firework or lightning example, we cannot tell that light is not traveling instantaneously. We can't tell that it took a finite time to travel from the source to us. But we do know that in astronomy because the distances are so much larger. So from the moon, for example, light takes a full second to reach us, as long as that boom took us to travel just 1,000 feet across the sky. So that means that we can call the moon 1 light second distant from us. So I think this terminology is a little bit confusing the first time you see it, but hopefully this is helping flesh it out. A light second sounds at first like a unit of time, but actually it's a unit of distance. It's the distance of the moon. Moving on to the sun, it takes 8 minutes to reach us from the time a photon is emitted from the surface of the sun until it reaches us here on Earth. That means that the sun is 8 light minutes distance away from us. Moving on to greater distance scales, our own Milky Way, the center of the galaxy, for example, 30,000 years. Anything that we see from the center of the galaxy, it took 30,000 years just to travel across the galaxy to reach us. So this illustrates how difficult interstellar travel is. Imagine even if you're traveling at the speed limit, at the speed of light, it takes 30,000 years to get across the galaxy. Okay, so the center of the galaxy, that means, is 30,000 light years distant from us. Now back to that galaxy, NGC 1068, also known as Messier 77, even farther, way outside our galaxy, a distant, distant galaxy, that's the 50 million years that it takes light to reach because it's 50 million light years distant from us. Okay, any questions on those preliminaries? All right, that concludes chapter 1.
I guess I may have a
Yep.
question, because I've heard that the sun absorbs photons before it gets out here, so so in some sense at the surface of the sun, that photon takes 8 minutes to get here.
Right.
But if the photon that gets generated inside the sun takes substantially longer to reach us.
Yeah.
Neutrinos, I think.
Yeah, great point. So I chose my words carefully. I said 8 minutes from the surface of the sun to us. It takes hundreds of thousands of years for that photon to travel across the sun. And that's not because the sun is big, but because it's bouncing around a lot. It's basically just like diffusing randomly, random walking, traveling throughout this ball of plasma, just bouncing around constantly until it finally escapes. So that's an interesting point. Any other questions, comments? Okay, so chapter 2, not as familiar a story. This is now a short time ago, but in a land rather than a galaxy far, far away. And that's Greenland. So 32 years ago, some innovative scientists, I can say that because I wasn't one of them, some innovative scientists, including here at Madison and also at UC Berkeley and also UC Irvine, decided to install some equipment into the Greenland ice. So really simple, if you've heard of photomultiplier tubes, these are like light bulbs in reverse. A photon hits the photomultiplier tube, generates a little bit of electric current. You can measure single photons. So they drilled a hole in the ice in Greenland, installed 3 of these light sensors in, and they measured particles, energetic particles, coming from the atmosphere, which in turn were generated by particles from the cosmos colliding with the atmosphere. And this is the foundation of the idea of IceCube and of the discoveries that I'm going to tell you about today. So simple project, just a handful of authors from these 3 institutions. The whole idea started here at UW-Madison, along with colleagues in California, including my PhD advisor, Buford Price. So they detected muons. We'll talk about what muons are. Fast forward another 10 years, now still a short time ago, but in a land farther away, land far, far away, in now not Greenland, but in Antarctica. the same set of scientists now collected a larger group of international partners, starting with Sweden, and then also additional countries, additional collaborators. Building on that original idea that you could detect particles in Greenland ice, they knew that you could also detect particles in Antarctic ice. And so they installed a larger array, several strings of these light sensors. You can see the dots there representing the individual light sensors. And now they detected neutrinos. Neutrinos coming from the atmosphere, again produced by cosmic particles colliding with the atmosphere, but now detected on the other side of the Earth, and neutrinos traveling through the Earth. So now, fast forward a few years from that, and I started my grad school time. And I started at a fortunate time when we were building IceCube, starting to build it, and I got to travel 3 times to Antarctica to help build this IceCube detector. So now IceCube is the successor to Amanda. After Amanda detected these neutrinos in the ice, the idea was proven that we could build a much larger detector and detect neutrinos not only from the atmosphere, but from beyond the atmosphere, from the cosmos. So really fun experience traveling to McMurdo and then onto the South Pole. Penguins on the coast at McMurdo Station, but not at the South Pole. South Pole's really high and really dry. It's almost 10,000 feet above sea level. That's 10,000 feet is almost all ice, and that's why our detector is there, because the ice there is basically the largest naturally occurring material that's very clear. So the clearest large body of material on Earth naturally occurring. That means that you can monitor billions of tons of ice for these neutrino interactions. So here's an aerial view of it. The runway, known as the skiway here, is where planes land on skis. You might be familiar with the dome that was iconic for many years. That was replaced with this modular South Pole station. And then a lot of the experiments that do astrophysics are across the skiway over here that do astrophysics and particle astrophysics. And our building that you saw on that first slide, the IceCube lab, is here. How did we build IceCube? We basically drilled into the ice by squirting hot water with as high temperature and as high pressure as we could. So here's another zoomed in aerial view. Hard to get a sense of scale, but this building is like the size of a small house, and so is this one. This is the drill tower. This is a giant cable spool, which is spooling the hot water hose down into the ice. And then here's the drill head that's hanging on that cable down into the ice, continuously squirting hot, high-pressure water. And this technology was all developed also here at UW-Madison, specifically in partnership between the physics department and the physical sciences lab in Stoughton. This was an amazing, simple idea, but an amazing engineering challenge and accomplishment. So after fine-tuning this drill, they were able to drill all the way down and all the way back up, 2 miles deep, well, 2.5 kilometers, 1.5 miles deep, 2.5 kilometers down and up again in less than 48 hours. Imagine doing that with any other kind of technology like mechanical drilling. Here's a video of what that looks like. The first 50 meters is snow, where if you squirt hot water, it's just going to leak out. And so there's a different drill technique that's used there. That's what you see here. It's just like a hot butter technique. Just circulating hot water in those copper coils that you could see. And now here's the squirting of the hot water beneath the snow layer in the deep ice. Keep doing this for a bit over 20 hours down, and then a bit under 20 hours back up. And then, so there were basically drill teams and then deployment teams, and we worked closely together during the construction. After the drill team was finished, the deployment team would come in, and I was part of that team, and our job was to now install the instrumentation. So here's what it looks to stand over a hole that's 2.5 kilometers deep, and that's 60 centimeters across. 60 centimeters is just a little bit wider than my shoulders. So it's pretty spooky to stare down this hole and imagine accidentally slipping and falling down 2.5 kilometers. Luckily, it's barely wider than a person's shoulders, and there's a protective lip around the drill tower, and so you'd really have to intentionally thread yourself down into that hole. You'd never be able to slip and fall into it, but it's pretty spooky to imagine. That reflective thing that you can see, that's just where the water level starts. So That's that 50 meters of snow that I mentioned. It doesn't start pooling until 150 feet down. So you'd fall 150 feet just through cold air before you even hit the water. And then another 2.5 kilometers down. So here's an aerial view of IceCube. Here you can see all the different strings. So we did this 86 times. Installed 60 of these light sensors on each of these strings, much larger scale than that initial demonstration in Greenland and South Pole that I showed you earlier. You can see the skiway, the new station, and the old station, and the layout of these 86 strings forming this grid. Each one an amazing engineering accomplishment, 2.5 kilometers deep, full of amazing instrumentation as well that I'll tell you a little bit about. So here's a view of that hole again in the upper left, but now one of those pieces of instrumentation going down in. This is a sphere that houses one of those photomultiplier tubes. It's a large one. It's about the size of a basketball, this whole sphere. And then it's, in addition to that giant sensor, it's filled with a lot of electronics that can control and read out the information. It's a huge international collaborative project. Here you can see some of the drillers in the bottom left, some of the deployers in the upper right, and this building, the IceCube lab. It's two different stories, if you can't tell. There's a row of windows up here and a ground floor here. And the cables come up out of the ice and in through these giant towers across these cable trays to connect to all the computers in here that do all the processing. And this whole project, from that initial idea and initial demonstration, is led through construction, maintenance, and operation ongoing today through UW-Madison. Here's an example meeting of, we now have over 350 scientists that contribute in lots of different ways between instrumentation, calibration, data processing, operations, data analysis, all really essential contributions, over 350 different scientists that are authors on our author list. And here's a meeting that we had. You might recognize this is outside of Memorial Union just last fall when we hosted those collaborators from around the world. So here's what IceCube looks like now that it's completed, an illustration of it. You can see those 86 strings, each with 60 of these light sensors, these digital optical modules. Now you can see a side illustration, that giant photomultiplier tube connected to the electronics that controls it and that reads out the information. It sends all that information back up over the cables to the surface. That giant building looks like tiny on this scale. Here you can see also the Eiffel Tower for scale. Massive project. Okay, so I've gone a little bit back and forth between the astrophysics and the construction. I haven't yet motivated exactly why we're doing this. So what are neutrinos and why do we want to detect them? We need to back up and do a little bit of particle physics 101 for that. And so here's the periodic table of particle physics. I always loved science, and especially biology and then chemistry, but always have and still have a terrible memory. And so I struggled in chemistry with the size of the periodic table, but I love particle physics because it's so much smaller. You don't need to remember very much. You can just remember some really simple symmetry principles, and then you can basically figure out all the contents of this table without having to memorize them. So all the normal, it's even simpler than it looks. All the normal matter that we are made of and that we experience day to day is made of basically just three particles, the up, the down, and the electron. So the up and the down are two different quarks. They combine in different combinations to make neutrons and protons. So if you like, instead, all the normal matter is made of neutrons, protons, and electrons. The neutrons and protons form into different types of atoms that then surround themselves with electrons to make, I should say, nuclei surround themselves with electrons to make different atoms. And now those different types of atoms, because of their different number of electrons, form the periodic table in terms of their different electrical behavior in chemical interactions. Now, in addition to those three particles, even though normal matter is made of those three, normal matter is also unstable. It can decay radioactively. And often when it does so, it emits a fourth particle, a neutrino. So lots of different nuclear decays and nuclear interactions more generally, including fission and fusion, and also including naturally occurring radioactive isotopes like uranium and thorium that are abundant throughout the Earth, naturally occurring also in this room in trace amounts right now. All of that produces nuclear interactions that include neutrinos. So you could say there's four of these basic particles. Now, for some reason that's an outstanding mystery, that basic structure of four particles is repeated another 2 times. It seems kind of redundant, but there's basically another whole column of 4 cousins that are very similar but just more massive. and then a third set of cousins, even more massive. Now, there are also these 4 particles that describe the interactions between these matter particles. That's the photon, bosons that explain how neutrinos interact in particular, and then the Higgs boson that was finally discovered about a decade ago. So neutrinos, compared to the quarks and the protons that they combine to make, are charged. Compare that to the photon, so is the electron. Compare that to the photon and the neutrino, which are electrically neutral. And that's really important because electrically neutral particles are not affected by magnetic fields, and they're not affected by electric fields. So neutrinos, rather, are electrically neutral just like the photon. That's really important. They also interact very rarely. We'll come back to that. Okay, so now what's the connection between these neutrinos and the light sensors that are in the ice? It's not obvious how you detect a neutrino with a light sensor. So here's another local photo. This was on the terrace about a year ago, a duck swimming across the lake in front of the terrace. And you can see it makes a wake behind it, this beautiful triangular-shaped wake. And that's because it's traveling faster than the speed of the ripples on the surface of the lake. If it were standing still and paddling its feet, it would just generate circles going out. But as soon as it starts moving forward, those circles basically add up to make this conical shape, or this triangular shape. There's a direct analog of that, which is charged particles traveling in a material. Instead of generating a mechanical disturbance, they generate an electrical disturbance. That means that they generate electromagnetic waves, that is photons. And that's known as Cherenkov radiation. You might have seen this in movies of nuclear reactors. So here's a duck enjoying the terrace. On the right is energetic particles enjoying a nuclear reactor. Okay, so now why is IceCube buried? Oh, to connect it to that. So when charged particles travel through the water or through ice, they make a flash of this Cherenkov radiation. Now, if a neutrino collides with the ice to make a charged particle, that charged particle can also travel through the ice to make a flash of light. So that's the connection. Neutrino to charged particle to flash of Cherenkov light to the detectors in IceCube. Now, why is IceCube buried so deep? It doesn't even start being instrumented until 1.5 kilometers down, and then continues all the way down to 2.5 kilometers. It's due to 2 reasons. One is that I said the ice is the clearest naturally occurring large amount of material on Earth. But if you take ice out of your freezer, it doesn't look like that. It looks really milky and opaque, right? And that's because it's full of bubbles. So if you, even after the snow layer at the South Pole, if you go deeper, it's ice, it's not snow, but it's ice filled with bubbles. And so it looks opaque, it looks milky. If you go deeper, the pressure increases so much that those bubbles are basically collapsed down into the crystal structure of the ice, and it becomes crystal clear. A second reason is muons that I mentioned earlier. These are from that second generation of cousins. These are the heavy cousin of the electron, and they're produced abundantly in Earth's atmosphere. They're raining down on us all the time, and they form a set of particle interactions that look a little bit like neutrinos, and so we need to go deep so that we can filter out those. If the deeper you go, the fewer the number of muons, and so you can identify the neutrinos more easily. So what's the connection between the neutrinos and muons and these charged particles that I mentioned that we detect? When a neutrino collides with an atom, it basically shatters that atom, and it can produce, it can do a couple of different things in that process. One is that it can produce a charged particle, the muon, that heavy cousin of the electron. And so the neutrino is basically gone now, and in its place is an energetic muon, which carries much of its original energy. That muon now streaks across the ice, and it's a charged particle, so it can emit that Cherenkov radiation that I mentioned. So here's a real event of a muon in our data. Each dot here is a location of one of these sensors, the PMTs, photomultiplier tubes, and the color is the timing. So it started at the upper left, and it went to the bottom right. And even just looking at it by eye, you can figure out that the muon came from the upper left, therefore the neutrino came from the upper left. Therefore, we can do astronomy with neutrinos. We can make a map of the sky by knowing all of these directions. We can do that within less than a degree, a fraction of a degree angular resolution. Another thing that the neutrino can do, I'm simplifying here, there are other things that they can do, but another thing they can do is produce a shower of particles. So that neutrino collides with the ice. Instead of producing a single muon, it shatters that atom, and it makes a shower of subatomic particles, many of which are charged. Each one of those charged ones can produce Cherenkov radiation, and so we see that emanating from this short, wide distribution of energetic particles. And because it's short and wide, the light deposition pattern looks much more spherical and much less like a long straight track. So by looking at this, it's a lot harder to figure out the direction that that neutrino came from. We can measure its energy very well. That's basically the analog of the color for a neutrino. So if you want to know the color of light, you want to know the energy of a neutrino. So that's really important. That's a great thing about these showers, also known as cascades. We can, with computational techniques, we can measure the direction, just not as well as with these muons. We can do it with a few degrees of angular resolution, between 5 and 10 degrees, rather than about half a degree for muons. Okay, so back to that picture of our 3 players, what are the signals and backgrounds that we detect? We're looking for these neutrinos, but they're produced in abundant backgrounds. When energetic particles collide with Earth's atmosphere, such as those that produce the aurora here, or at higher energies, ones that produce showers in Earth's atmosphere, they produce energetic particles, not in the ice, but directly in Earth's atmosphere. And that happens when cosmic rays, which are protons or other energetic heavy particles, like atomic nuclei, when they collide with the atmosphere, they make this shower of particles. That includes neutrinos and muons, and those can then reach the detector. Muons I mentioned before, that's why IceCube is deep, so that we can reduce the number of these muons. They also produce neutrinos from the atmosphere. So that's one fundamental challenge, that we have to try to identify our neutrinos from the cosmos separately from the neutrinos from the atmosphere. Question?
Yeah, is that light, is that the aurora australis?
Yep. Not the aurora borealis, the aurora australis, above the IceCube detector. Yep. Produced by lower energetic particles interacting in Earth's atmosphere. Okay, so there are these atmospheric muons, which are background, 70 billion of those per year. Atmospheric neutrinos, about 1,000 times fewer of those. And then astrophysical neutrinos, the ones we're interested in, 1 in 100 million. So it's really a needle in a haystack challenge to identify the signals and separate them from the backgrounds. Okay, so we have another interlude now to explain the benefits of neutrino astronomy. So I've explained how we constructed IceCube. I've explained what neutrinos are. Next question is, why are we using neutrinos to do astrophysics? To do that, we need to back up and think about light and the different types of light. So I think we've all studied the color wheel. It goes in this nice circle from red through yellow, blue, back to violet, and then back to red. But that's just a small piece of the story. These are all photons. They're also waves, in other words, electromagnetic waves. They span this whole spectrum. These are all the different colors that we can see. But beyond that spectrum is a whole spectrum, and a larger spectrum, like a whole universe out there, a vast spectrum beyond what we can see. So you might have heard about other animals that can see in the infrared or in the ultraviolet. They can see slightly beyond what we can see from the red through violet. If you go beyond the violet, you get to ultraviolet. If you go beyond the red, you get to infrared. But you can keep going. Beyond the infrared, you can go to even larger wavelengths, to microwave and radio radiation. Beyond the ultraviolet, you can go to even shorter wavelengths, to X-ray and gamma radiation. And so there's this vast amount of electromagnetic spectrum where there's very different information from what we can see with our own eyes. Humans can only see about a factor of 2, an octave in wavelength, and the electromagnetic spectrum spans dozens of octaves. So there's a huge amount of information out there beyond what we can see with our eyes. So if you look at a person in visible light, if you think about why you see them, you're seeing photons that are bouncing off of the surfaces that you can see. The photons are being emitted by some light source, like the ambient night sky in the window or a light source in the room. They're bouncing off the surface of the person and the clothing and so on. And the color that you see depends on that interaction, that scattering of the photon on the surface, whether it's absorbed or whether it's reflected, in other words, scattered. If we turn off the light or the sun outside, this is what that scene looks like. So it really relies on the scattering properties of the light and that person to interpret this scene. and it depends on having a source of light. If you used, so that's scattering. If you used infrared vision, here's what that same scene would look like. Very different information, and you don't actually need a light source in the room or outside to see this scene. So this is what we're seeing here is emission. It's not just scattering of the surface, by the surface of photons, but it's direct emission of infrared light by the person because of the different temperatures of the emitting surface. So here you can see the exposed skin is very bright. Infrared, remember, is closely related to heat and temperature. The clothing is blocking some of the infrared, so it's not as bright there. The glass of the glasses is blocking a lot of it. That's the greenhouse effect, basically, the same reason that the car is hot on a sunny day and that greenhouses work. So the physics here is the physics of scattering and emission of these particles, really important. Now, if you were to ask a typical person what an X-ray is, they might say it's, well, before I come to that, if you look at a person's hand, it's the same thing as that previous scene. A photon bouncing off of the surface, not going very deep, scattering or being absorbed immediately. The color that you see depends on those interaction properties, that scattering. If you ask a person what an X-ray is, they'll probably say an image that you get at a doctor's office or a dentist's office. But if you ask a physicist or an astronomer, they'll probably say it's a photon or an electromagnetic wave. So here's what one of those images would look like in the X-ray. Now this depends on a source of X-rays, like the light case where we had an ambient source of light, and then we saw the light bounce off the person's face. But here it depends on not just the source of the light, but also, rather than scattering, it depends on absorption. So the bones absorb the X-rays, the soft tissue does not. And so we can reconstruct, we basically illuminate the hand with a source of X-rays, then have film on the other side, and we can make this map that indicates which parts of the image transmitted the photons, the X-rays, and which parts of the map did not. And we can therefore infer the interior of this object. Completely different view than what we get from photons bouncing off the surface of it. So the three physics processes that are really important here for each of these types of light, infrared, visible, and X-ray, is scattering and absorption, and emission in the case of infrared. So keep in mind these basic processes: emission, scattering, and absorption. And which one occurs depends on the nature of the messenger, the particle, the photon, that is its energy or its wavelength, and also on the material that it's encountering. So we can tell a lot about the material by the information of the signal carried by the messenger. So that brings us to neutrinos. Neutrinos are an entirely different messenger. They're like super X-rays. If we think about those three properties, emission, scattering, and absorption, neutrinos are emitted very abundantly, but they have very, very little absorption. That was one nice thing about X-rays. They can travel straight through tissue as long as it's not bone. And they have very, very little scattering. So completely different information, not only from visible and infrared and X-rays, but from the entire electromagnetic spectrum. So neutrinos can travel through the entire Earth, even through other dense regions of the cosmos. They're like super X-ray vision. So where do neutrinos come from? The graph here shows basically the probability of a neutrino interacting, that is scattering, as a function of energy. So it's more likely at the highest energies, less likely at the lowest energies. And we think that they're produced in the Big Bang here on Earth, in human devices, including reactors and particle accelerators, in exploding stars, in stars themselves. And in IceCube, we're especially interested in the galaxy itself and the cosmos beyond the galaxy. Here's another view of that, but now instead of graphing its probability of interaction, we're graphing the abundance of the neutrinos, the rate of them reaching the Earth. And so even though the probability of interaction grows with energy, the abundance of the neutrinos decreases with energy. So that's the challenge that we're facing. We want to detect these very high energy these very high energy neutrinos, but they're very rare at the highest energies. That's why we need 1 billion tons of ice in IceCube. So here's that electromagnetic spectrum, the single octave that humans can see, and then zooming way out in the electromagnetic spectrum, not only that, in the particle spectrum into IceCube. So here's different types of astrophysics that has now been done across the electromagnetic spectrum. And now we're extending that into the even higher energy range, shorter wavelength, into gamma ray particles and also neutrinos with IceCube. Okay, so when IceCube was first constructed, after about a year of operation, we started seeing some very high energy events. If you remember the illustration of IceCube, it's a kilometer across, and this single neutrino interaction lit up the entire detector. That means that it's a very high energy particle, about 1,000 TeV. TeV is the unit of energy that particle physicists use. And this is hundreds of times more energetic than the typical particles at the highest energy human accelerators. So we discovered that the universe glows very brightly in these neutrinos at these very, very high energies, orders of magnitude more energetic than humans can accelerate particles here on Earth. So the universe glows very brightly in neutrinos. We can quantify that in a graph like this. The vertical axis tells us the abundance of the neutrinos, the flux of the neutrinos, and the horizontal axis tells us the energy of those particles. So in the middle here is the neutrinos in pink. To the left is gamma rays, the highest energy type of light, and to the right is these cosmic rays that I mentioned, the high energy protons and other nuclei. And the fact that they're all on the same vertical scale tells us that there's either some fascinating coincidence or that there's some deep connection between them. In any case, the universe is very bright in neutrinos in addition to being bright in light, including gamma rays and energetic particles. So neutrinos are a key part of this experience of understanding the universe, analogous to the lightworks show that you need to both hear and see the fireworks. Okay. Now, so there's some deep connection in terms of the energetics. However, the universe looks very different in each messenger. So I'll show you what it looks like. So here's the universe in neutrinos. It looks like a uniform sky full of noise, and most of it is. It's a lot of neutrinos from the atmosphere that I mentioned. However, there's some individual excesses, hotspots of excess neutrinos that we think are coming from astrophysical sources. One of them is this galaxy that we started with far, far away a long time ago. This is this galaxy, Messier 77, also known as NGC 1068. So that was a hotspot in this map of the entire sky in neutrinos. Now, how do I identify if these hotspots are significant or not? There's a lot of information, there's a lot of work sort of beneath the hood, behind the scenes, that I don't have time to tell you about today. But I just want to give you a glimpse of it, and a lot of this is happening here in UW-Madison. This is how we calibrate our detector. So even though the ice there is a very clear material, it does have very small amounts of dust and of volcanic ash, and that varies coherently as a function of depth in the ice. You might have heard about ice core drilling, where you can use ice cores as a time machine to understand glaciology and climatology back up to hundreds of thousands of years ago. IceCube is the same thing. We have these layers of dust and ash, and we can use it to understand glaciology and climatology. And more importantly, for astrophysics, we need to understand it to understand the propagation of light, of Cherenkov light through the detector. This is just one example of all the technical work that needs to be done to understand our detector. So here's mapping out this amount of light scattering as a function of depth inside of the detector. After doing all of that technical work, calibration, data processing, reconstructions, and so on, we detected this galaxy. So we can indeed say as of this fall that this detector, this galaxy NGC 1068, Messier 77, is a neutrino source, and it's sticking out above this atmospheric background. That was an announcement, a result that we published back in November. Any quick questions on that before we go to chapter 3? Okay, so now we get to chapter 3. Not a long time ago in a galaxy far, far away, we already did that, but now we're a medium time ago. What's medium? Maybe 30,000 years? That timescale should sound familiar. In a galaxy nearby, 30,000 light years. That distance scale should sound familiar. So here's what the universe looks like now in visible light. In particular, you can see this is the full sky, so northern hemisphere, northern galactic plane, I should say, in the north, southern galactic plane in the south. This is a coordinate system where the galactic plane is running straight across horizontally. And so that's the galaxy. You can see it's shining really brightly in stars, but also has these lanes of dust that are absorbing light. You can see the Magellanic Clouds off of the plane. You can see other galaxies far away. So that's visible light. Remembering the analogy with infrared and X-ray, The universe looks, just as people look very different in different wavebands, the universe looks very different in different wavebands. So here's the universe in infrared light. You can see the Magellanic Cloud shining really brightly here. You can see our own galaxy shining brightly. The center of the galaxy is shining really brightly. These lanes of dust, again, the dust itself is glowing brightly. The regions of stars and star formation are also glowing brightly. That's going to infrared, to longer wavelengths. Going to even longer wavelengths, again, like an X-ray, if you ask a typical person what a microwave is, they would say a device to cook your food. But if you ask an astronomer or a physicist, they would say a type of very short radio wave. And so here's the universe in very short radio waves, microwaves. This is a view of the entire universe in these microwaves, and that's the cosmic microwave background. So that's dominated by the glow of the Big Bang itself. That's what we're seeing. So you can see very different information from very different bands. Coming to more traditional radio waves, longer wavelength, you can see this beautiful, large, wispy structures sticking up above the plane of the galaxy. The plane of the galaxy itself really bright in radio waves, but also these large structures extending above it. That's mostly produced by energetic electrons whizzing around and radiating radio waves. So that's going to the longest part of the electromagnetic spectrum. Zooming back through infrared, back through visible, on beyond visible, we get to ultraviolet. Here's a view of the ultraviolet sky. This is one of the bands where it's actually least explored. This is just a map of where one of the main telescopes has pointed and what it has seen in those directions, but it's a pretty incomplete view. Again, we can see the galaxy. Ultraviolet means really hot, so like very young stars, for example. Again, the Magellanic Clouds and our own galaxy. Going beyond ultraviolet, we get to X-rays. These are now a lot of binary star systems, for example, that can act as particle accelerators. Two stars that are whizzing around each other, accelerating particles. Again, we see the Magellanic Clouds and our own plane of our Milky Way. Beyond X-rays, we get to gamma rays. Here's the view of the universe in gamma rays. You can see the Milky Way again, and now we see, like in some of the other bands, you can see both kind of a cloudy, diffuse structure and also individual points of light in the galaxy and also beyond the galaxy. So beyond the galaxy, these are other galaxies that are shining brightly in gamma rays, acting as particle accelerators. Within our galaxy, they're both individual particle accelerators, individual objects, and this diffuse gas-like emission. Putting that all together now, zooming in on the plane itself, we can make this single image combining all these different views, and this is the power of what's known as multi-wavelength astronomy. So just zooming in on the plane of the galaxy itself, you can see this very different view of the galaxy, telling us totally different information about the galaxy in all these different wavelengths. And now we bring in the neutrinos. So here's that picture of the universe in neutrinos that I showed you before. We've now detected this distant galaxy 50 million light years away. That's using muons. Remember, there are two different types of signatures that we can see of neutrinos in the detector. Muons, but also cascades or showers. So this is the view of the universe in neutrinos through muons. Now we're also starting to image the universe in neutrinos through cascades. And this is what it looks like. So this is now a slightly different coordinate system. So instead of showing the plane of the galaxy running across the center, this is taking the Earth and projecting it outward, because the IceCube detector views the sky very differently in the north compared to the south. And so it's useful to plot it this way. So in this case, the plane of the galaxy is running along this black line, making this kind of smile shape. And you can see by eye, there's more emission along that plane than out of it. Not as obviously as for photons, but you can see it. In particular, this dot at the center of the black line is the center of the Milky Way. And you can see this emission that's kind of clumpy, but clustered more towards the center of the Milky Way than other parts of the Milky Way or other parts of the universe. So this is the emerging view of the universe, including the Milky Way in neutrinos. Totally different information than we've got from all the different bands of the electromagnetic spectrum. So pulling that together, here's, again, that optical visible light image of the galaxy. Here's now the gamma ray view. This is individual points of light from astrophysical objects in the galaxy, as well as this emission from clouds of gas within the Milky Way. To elaborate a little bit on that, one of the important mechanisms of this gamma ray emission is from the energetic cosmic rays that we know are protons and nuclei, but we don't really know what they're coming from. We know that those are throughout the galaxy, and they're colliding with gas within the galaxy. When that happens, they undergo a particle physics interaction that produces the gamma rays. We think that should also lead to neutrinos. And so based on that process, we make a model of what we think, if we had a perfect neutrino telescope with perfect vision, what we think that would look like. So this is a model. It looks like this. And then we make that more realistic by smearing it according to, we know that we don't have perfect vision because of these neutrinos being hard to detect and being hard to calculate exactly what the direction each one came from was. And so this is what we think the idealized average view of the sky should look like from IceCube. And this is what it does look like. So this top expectation in the bright yellow is averaging over statistical fluctuations. And then the bottom one is the real view of the sky, including statistical fluctuations and where we detect neutrinos from and where we don't. But you can see those neutrinos are clustered in this inner galaxy. You can see the coordinate system now here. This is distance along the galaxy from the center all the way to the anti-center on one side, and then going in the other direction all the way to the anti-center on the other direction. And so you can see there's definitely an excess of neutrinos in the center region compared to the outskirts. And that's what we expect according to this model. Okay, how do we trust this measurement? It was made possible by some really interesting innovations using machine learning. That's how a lot of these measurements are made now in our field and a lot of related fields. So how can we trust it? Is the computer just acting like a black box? Is it just telling us that it detects the galaxy because it thinks we want to detect the galaxy? Here's how we do a rigorous measurement to make sure that's not the case. The nice thing is that with IceCube, we can simply randomize our data. So we can scramble it, maintaining all the detector distributions, but comparing basically a randomized control sample to the actual sample that we measure. It's analogous to a randomized controlled trial in Madison. On the right is what we'd expect if there was no signal. If we just had random distribution, on the right is what we actually see. So you can see a big difference between the two. That's telling us that there are more neutrinos from the galactic center than we expect by chance. And we're doing that with a really simple statistical method after all the machine learning stuff is done, so it's not affected by any of that. So what's the color of these neutrinos? If you make a map of the sky in light, you want to know the different colors. In neutrinos, we also want to measure the colors, but I mentioned before we call that the spectrum. So that's the energy distribution of these neutrinos. We've previously measured the neutrino glow from the entire universe. That's this hashed band here. The vertical axis is the amount of neutrinos. The horizontal is the color or the energy of the neutrinos. And now we've also measured our galaxy. It still has a lot of uncertainty, and it depends on what you assume about the shape of the signal. But you can see it's one of these bands. So it's about 10 times less bright than the entire universe. Still pretty bright to compare our galaxy to the rest of the universe. And now we basically understand both the local universe, our galaxy, and the total glow from the other parts of the universe. I should say we understand the color, the energy distribution. It's still a very open question what's actually producing both of these two components. So what is producing the neutrinos? Is it individual astrophysical objects that emit cosmic rays and neutrinos, like those points of light that were in the gamma ray map? Is it that diffuse process of cosmic rays colliding with gas in the galaxy? Probably, yes, probably both. So there are good reasons to think that both of those are contributing to the signal that we see. Right now, they're both consistent with the data, so we don't know which one it is. Probably they're both there in some level. We don't know which one is dominating. We don't know the relative contributions of both. A postdoc here at UW-Madison, Abhishek Desai, has been working on that question. So he's been simulating what the galaxy would look like, what the universe would look like, including all these galactic sources, and then interpreting that in our data. So if you have a certain number of neutrinos in a certain number of sources in the galaxy on the horizontal axis, and you calculate how many IceCube would detect on the vertical axis, you can see the correspondence. So if there were only 2 or 3 neutrino sources in the galaxy that were making the entire signal, we would have seen those. N detected would have equaled N sources in simulated. We would have detected them as individual sources. We did not. We only see this aggregate from the entire galaxy. Because we only detected less than one individual source out of that entire total galactic glow, that means that this curve must have come up and then gone down again. So there must be at least 10 sources. So we can say there are more than a handful of sources if they're produced by sources. It could also be produced entirely by this diffuse gas process. Okay, so here's a complete timeline of some highlights, some milestones in neutrino astronomy. I didn't cover all of these, but just to remind you a few of the highlights. Atmospheric neutrinos were first detected 2 decades ago by that predecessor, Amanda, at the South Pole. Before that, muons were detected in Greenland. IceCube was completed then about a decade ago, a little more than a decade now. As soon as the data were analyzed from the full detector, just within a couple years, the first evidence for this glow of neutrinos from the universe was discovered, astrophysical neutrinos. Skipping over a couple that I didn't have time for today, in the fall we announced the source NGC 1068, this galaxy 50 million light years away. And now we've also detected emission from our own Milky Way, our own galaxy. So what's the next milestone on this? Hopefully they'll keep coming. It's nice to see that they're happening, it seems like even more frequently than in the early years. So let's keep our fingers crossed. But we're not just waiting for more running of this detector. We also want a bigger, better detector. These neutrinos do interact very rarely. Most of them travel all the way through the Earth. It's only about 1 in a million that reaches IceCube, that actually collides with an atom inside of IceCube. And so we need a bigger detector. So with apologies for a second sci-fi reference, this is the next generation, IceCube Gen 2. So IceCube is this hexagonal footprint at the middle, and we want to expand with an 8 times bigger detector for less than 8 times the cost, because we're going to space them much larger and use all the technology lessons that we've learned from building IceCube the first time around. So larger spacing between the strings, much better instrumentation on each string, and we'll be able to operate this even bigger and better detector, IceCube Gen 2. There's a huge amount of IceCube science that I didn't have time for today. I really just focused on a couple different parts of it today. That's one of the most fun things about working on it. It's a really not just multinational, multi-continental, but multi-interdisciplinary project. I'm most interested in astrophysics. That's what I focused on today. Lots of different types of astrophysics we do. But we also do neutrino physics, earth science that I referenced briefly, exotic physics, dark matter. We might be able to detect dark matter using neutrinos, and fundamental physics. So it's been almost a cliche in our field now for a while that we're opening new windows on the universe. And so a graphic designer at our institute downtown made this analogy real with not quite real, but made it physical with an illustration of stained glass representing the windows on the universe. You've probably, in addition to neutrinos in the last week, you've probably heard about gravitational waves in the news in the last week and also in the last decade. That's an exciting new window on the left. In the middle is neutrinos, and on the right is the electromagnetic spectrum, including gamma rays. And just recently, we made that diagram of these windows a little bit more real by printing it very large and mounting it in our institute downtown near the Capitol Square. It's not quite stained glass, but it's a nice illustration of stained glass. So we're now doing astronomy with both neutrinos and gravitational waves, in addition to the electromagnetic spectrum, all the different types of photons. We call this multi-messenger astrophysics, and it enables this much more complete experience and understanding and view of the universe, like experiencing fireworks with both light and sound. First thing we discovered is that the universe glows brightly in neutrinos. Now we've also detected neutrinos. I didn't mention this, but previously scientists have detected neutrinos from the sun and from a supernova. Now with IceCube, also distant galaxies and our own Milky Way galaxy. So in a lot of astronomy, we divide it into galactic and extragalactic astronomy, and now with IceCube, we're doing both types of astrophysics. Thanks.
All right, thank you so much. I will be walking around with the mic so those online can hear the questions. So if you want to just raise your hand and I'll bring it to you.
Why is NGC 1068 emitting so many neutrinos?
It's a great question. Can you tell me? Okay, well, so it's a special galaxy. So we think that most galaxies, pretty much all galaxies, have a giant black hole at the center. Now, our own galaxy has one. It's been measured to be 4 million solar masses. People just got a Nobel Prize a couple years ago for the people who measured that. For some reason, our own galaxy, the black hole at the center of it is quiet. It's quiescent. It's not emitting a lot of particles and radiation. Now, the NGC 1068, this other galaxy, for some reason, its black hole is very active. And probably that's because there's matter falling down into it. And then that matter is somehow an energy source, which is then causing radiation and matter and neutrinos to be spewed out. Exactly how and why that's happening in some galaxies and why some are including neutrinos and some are not is an important question that we'll hopefully be able to answer by combining the neutrino information with photons and radio waves and the full electromagnetic spectrum. But it's still an open question.
So when you make it larger, will you have more correlation with ANITA in the microwave region?
We hope so. So ANITA is a balloon-borne experiment that circles around Antarctica, and it's looking for even higher energy neutrinos. And yeah, in my group, we've done some studies where we're looking for neutrinos from the same sources that ANITA might be seeing neutrinos. We call that, like we saw multi-wavelength astronomy in the electromagnetic spectrum, we call that multi-messenger neutrino astronomy.
Is there a reason why the patterns from the radio wave image of the Milky Way, where the electrons are zooming around, are shaped the way that they are?
Yeah, let me pull that up. Some of it's probably relatively local structures. So for example, keep in mind this is one image of the universe, taken in the last few years. We know that it's variable in lots of different timescales, but we don't have, except for on human timescales, we don't have images on longer timescales. So probably this is a very dynamic picture where there are explosions that have happened, like supernovae. They've produced populations of energetic electrons in certain distributions, and then those electrons are what are producing the radio radiation. Yeah.
Yeah, thanks. Yeah, two questions. First of all, how realistic is it to be able to map the universe as you're doing here on a flat sheet? I mean, when so little is known really about the shape and the dimensions of the universe. And then a slightly different question. Are the South Pole stations, are those under U.S. or international control? And where is the Russian Vostok station located in relation to the South Pole station? Thanks.
Thank you. Okay, the first question was about the projection. How fair is it to represent the entire universe on a simple oval like this? I think that's a great point. It's easy to lose sight of how complex it all is. So first of all, there's the projection of the 3D onto a 2D. As you know from mapping the Earth, that produces distortions, so you have to always keep that in mind, like around the edges. This point is really wrapping around connected to this point, and it's highly distorted close to the edges. This is one particular projection that we use a lot that we think minimizes some of those distortions, but that's important to keep in mind. A bigger thing is the third dimension is not shown at all. The distance, and that's often a problem depending on what waveband you're working in. You might have no idea what the distance is. This dot and this dot look like they're close to each other, but they might be vastly at different distance scales, even though they're close to each other along the line of sight. And then the shape of it, that's something that we think the universe is pretty flat from measurements in cosmology, but what it looks like near the beginning at the Big Bang, that's definitely an open question. The second question was, is the South Pole station operated internationally or by the US? The station itself is the US National Science Foundation Amundsen Scott South Pole Station, so that's under US jurisdiction. The land surrounding it is international. It's a little bit analogous to international waters. The land surrounding is international, but the station itself it's like if there's a US boat in the middle of the ocean, there's US jurisdiction on the boat, but not in the water surrounding it. And Vostok is a few hundred miles away from South Pole, to the north.
All right, we have a question on Zoom. Can you tell us about how the cosmic neutrino background and the prospects of IceCube detecting it?
Yeah, the cosmic neutrino background. So the cosmic, if it's the one that I'm thinking of, so there are different people refer to the cosmic neutrino background as different things. What we usually refer to that as is the analog of the cosmic microwave background. So this is in the early universe, after the Big Bang, the universe, the matter in the universe was this hot plasma of electrons and photons and protons, and there were photons that were emitted that were then stretched as the universe expanded and became this radio glow, these microwaves. We think that neutrinos were also part of that hot soup. And so that direct remnant from the Big Bang is the cosmic neutrino background as opposed to the cosmic microwave background. And that's very, very low energy. Like IceCube is very, very high energy. And like this is very, very low energy photons. And so IceCube itself, unfortunately, has really no prospects for ever seeing that cosmic neutrino background, even though it's very abundant, like hundreds of these neutrinos per cubic centimeter.
So maybe this is a dumb question, but can you explain like what's the meaning of there being more neutrinos in some part of the cosmos and less somewhere else?
Yeah, it's telling us something about what's producing them. You know, so far we know that the universe is producing neutrinos. We know that it's very bright if you compare it to the other signals, almost surprisingly bright, basically as bright as the most optimistic theorists had predicted, that motivated the size of IceCube. And yet it's taken us a long time to detect the first sources. So that means that there are very many sources out there. If you think that the universe as a whole is really bright in neutrinos, and yet it's hard to see the individual sources, that means that there's a large number of dim sources rather than a small number of bright sources. Otherwise, we'd see those small dots of light really brightly right away. So we are starting to see the individual sources outside the galaxy. That's exciting news about this one galaxy, NGC 1068. And now that we're starting to see the galaxy itself, that also opens interesting studies that we can do with that. But again, with the galaxy, it's not like we saw, like if you go outside in the middle of the day, you see the sun. You know there's only one star nearby that's really bright. You don't see two stars, you don't see multiple stars. In the galaxy, we didn't see one or two bright sources. We see this, what so far looks like a diffuse glow with maybe a little bit of clumpiness yet, but so far we can't really say what the origins of that clumpiness is. Hopefully with better data and better methods, we'll be able to identify the individual sources in the galaxy as we're starting to do outside the galaxy.
Oh. Earlier, you were saying that the universe is mostly flat. Why is it flat?
Okay, why is the universe flat? I think a theoretical cosmologist might have a good answer for that. I would just say that we measured it to be that way. I don't have any deeper reason. I think it's exciting that we can measure such things about not only the size and contents of the universe, but also its shape. But I don't have a deep explanation for why. I think we could have measured it and it could have turned out to be other ways.
I just have a very simplistic, hopefully this is not too naive here. I just found in the Google, Scientific American, mysterious neutrinos get new mass estimate. Now, if it's got a mass, can't really travel at the speed of light. Now, can you be actually looking at maps at two different time frames?
That's a great question. Yeah, so one reason that that light travels at the speed of light is because it has zero mass. Neutrinos, I mentioned, have very low mass, but not zero mass. So they do travel slightly slower than the speed of light.
So the difference may be just at two different time frames.
Yeah. Now, if you do the calculation for these sources that are within 50 million light years, we've even have evidence of a source that's even 100 times farther. If you do the calculation of the delay time, it's still very, very small due to this mass. And so there are other more speculative ideas that not just because of the mass of the neutrino, but actually because of the nature of space-time itself, if you have a neutrino at a different energy, it may be able to see the structure of space-time differently at higher energy than at lower energy. And so their idea is that you can measure those possibilities, those imprints, through distortions and time delays in the neutrino signal. But we don't have any experimental evidence of that yet.
I read.
Sorry, one more quick thing on that. You can also ask the question, if there were a delay in such things, due to such things, then we might have seen the neutrinos arrive much later than if they were traveling at the speed of light. And we've done that search and we have not seen any such things.
If we live another 10 million years, we may actually fill in more of the gaps that you see in gamma ray map.
Maybe, if the galaxy is getting brighter and we just haven't seen that yet, for example, or other more distant sources that emitted a while ago and that signal hasn't reached us yet. Yeah.
In the articles I've read in something like the New York Times, I give you a comment on this because I was looking at that information, and in discussing the IceCube project, what I was surprised at is the University of Wisconsin was never mentioned in these articles. Why would that be, considering it's been one of the big drivers there?
I was also surprised by that. Maybe you could write them a letter and update them. It's a very large international project, and there have been important contributions from lots of universities around the world. We led the design, construction, and operation and maintenance, but it's really a team project with hundreds of people making important contributions, each of them, and dozens of universities and dozens of, a couple dozen countries.
One other piece from I think it was the New York Times, it was a discussion about some new information, but they seem to indicate that a lot of this new information was derived from reanalyzing a lot of the previous data over a period of 10 years. Were you involved in that, and what kind of additional analysis was being done in order to eke out more information?
Yeah, we organize our data analysis into working groups, and I was co-leading the working group that made both the NGC 1068 measurement and this new one. But it's large collaboration with lots of members of the team contributing, and especially the analysis itself was led by a German university on Drexel. I think that's why a lot of the coverage that you saw was of those universities. So what happened after this decade of data? There were new innovations in how we identify these shower-like particles and separate them from backgrounds, being muons especially, atmospheric muons, and also new innovations on how we estimate the direction of each of these neutrinos. And those were using the machine learning methods that I mentioned earlier. So it's not just, that's really the key to both of these breakthroughs, not just waiting for more data, but learning how to use and understand our data better.
When do you project the extra holes, the extra detector to be done?
It depends basically on when it's funded. So we're doing research and development now. A lot of students and postdocs and engineers and scientists here in Madison developing the improved instrumentation for that. We're also, in the meantime, we're doing an upgrade that's not quite the new generation, but it's called the IceCube upgrade. And that's a project that's already underway and will be installed in a couple years. And then basically building on the success of that, we'll start construction pending funding on this next generation IceCube Gen 2.
Yeah, two more questions. First of all, what are the Magellanic clouds comprised of? And another question, are you involved at all with the other Antarctic project that deals with core sampling for oxygen isotopes?
Okay, yeah, the Magellanic Clouds are two small nearby galaxies that both happen to be in the southern sky. And they're basically normal galaxies like ours. They're just smaller. And there's a really interesting, if you simulate basically the evolution of the universe, then galaxies naturally form and assemble into these hierarchical structures where they're clustered. And so you expect that galaxies form not uniformly distributed, not randomly distributed, but in these hierarchical clusters. And so basically, the Magellanic Clouds are called satellite galaxies of our galaxy. The other question was if I'm involved at all in ice coring. No, I'm not. It's fascinating science, and we contribute a lot to glaciology studies through our calibrations. And the group I was part of in grad school at UC Berkeley did a lot of that, but I'm not involved in that personally.
A question about the actual layout of the IceCube, the detectors and the holes. And with all, how many detectors in total and all that?
There's 86 strings, each with 60 sensors, so about 5,000 sensors.
Oh, wow. And they're, you know, electronically, I mean, laid out, like when a neutrino goes through and it lights up and, you know, it's hitting multiple, or the light's being detected by multiple sensors. And then you have like timing, assuming, you know, so you can detect, you know, the timing it reaches everyone. And then you can lay out the direction, the path of it through through the detectors. And that's if everything is laid out like in a perfect matrix.
Yeah.
But I have to assume if you're drilling in the ice 1.5 miles with just basically free-falling hot water drill, do those deviate at all in 1.5 miles? And then you don't really have this perfect cube structure. And then how do you compensate for?
Yeah, good question. So basically, how do we calibrate the exact position of each of our sensors? That was one of my jobs during construction. I had to hang my head over that hole with like the cold updraft air coming, and with a laser ranger, and basically I would measure the distance from each sensor to the next sensor as we installed it. So that was one degree of freedom, the distance between the sensors. You asked if the drill is walking basically horizontally during the drilling, and basically it's hanging surprisingly plumb because it's a pretty heavy weight on a very long string. And so we measure that throughout the construction, and it's within about plus or minus half a meter. We also validate that later with calibration devices inside the spheres. We flash light from one sensor to the others. And simple timing calculations, like I mentioned at the beginning of the talk, you can measure directly the position, the 3D position of each of the sensors that way. So that's one of the fundamental calibrations. That's actually one of the easiest ones going into all of these measurements.
I have a question about if you're knowledgeable about the history of electromagnetic compatibility with the instrument, and when you make it larger, are you going to have any more issues with electromagnetic interference?
Yeah, I think the question was if there's electromagnetic interference between our instrument and other instruments. Yeah. There are some people who study, actually related to that Aurora Australis, people who study the ionosphere. And one way they do that is by having this really giant, long antenna that's buried in the ice and shooting ultra-low frequency radio waves into the atmosphere. And that caused problems for us because our strings were acting as antennas and picking up that noise. But we talked with them and basically coordinated, and that's not causing problems anymore. That was years ago. I'm not sure if they're still active or not. It's a constant, yeah, it's something we need to be aware of. You know, there are a lot of experiments, a lot of observatories working in Antarctica. Also, some of them, those measurements of the cosmic microwave background are working there. And we all need to stay in touch with each other to make sure we're not causing electromagnetic noise that interferes with one another. It's actually called the quiet sector of Antarctica because of that. It's radio quiet.
All right, are there any more questions? All right, thank you so much for speaking. Such a great talk.